Welcome back to the Deep Dive, where we tear into the latest research so you don't have to. Today, we are tackling a really fundamental challenge for AI developers. It's this idea of the digital memory wipe.
It really is the central dilemma, isn't it? You spend all this time and, frankly, a massive amount of resources pre-training a model on billions of data points. You make it an expert.
A well-rounded expert, yeah.
And then the very moment you try to specialize it on a single task to make it useful, it starts to forget everything you just taught it.
Exactly. And that's our mission for this deep dive. We're getting into an empirical study on something called catastrophic forgetting, or CF, during instruction tuning. We really need to understand why some of these incredibly powerful models get sharper in one area, but, well, a lot duller everywhere else.
So to start, let's just be crystal clear on what we mean by CF. It's not like the model is running out of memory. It's this phenomenon where, as a model learns new things sequentially, it just abruptly loses knowledge it already had.
It's like it's overriding its own brain.
That's a perfect way to put it. You're overwriting critical neural network parameters with new information, and that erodes its general skills.
I always think of it like training a brilliant historian to become, say, an airline pilot. You want them to learn to fly, but you really, really hope they don't forget who won World War II in the process.
That is the trade-off. And this study was very careful about what kind of forgetting it measured. They tracked three really critical categories of general knowledge.
Okay.
First was domain knowledge. This is your basic factual base. They measured it using the MMLU benchmark, which covers STEM, social sciences, you name it.
So basically, did it forget its university education?
Pretty much. Second, they measured reasoning. This is common sense logic, math problems, dialogue coherence, all the things that require putting facts together.
Okay, so not just what it knows, but how it thinks.
Exactly. And third, and this is a big one, reading comprehension using the RACE dataset. So can the model still understand complex high school or college level texts after you've retrained it?
And they put some serious models through the ringer here, right? We're talking about LLMs like BLOOMZ and MT0, up to around 7 billion parameters.
Yep. And they didn't just teach them one new thing. They trained them sequentially on 5 different instruction tasks, things like text simplification or headline generation.
That sequential part feels really important. It mimics how these models are used in the real world, constantly being updated and fine-tuned.
It's key. They had to see if the knowledge eroded bit by bit or all at once.
So after all that, what was the verdict? Is catastrophic forgetting a real thing?
Oh, it is undeniably real. The study confirmed it's a pervasive issue across every single model they tested, from 1 billion to 7 billion parameters.
And they had a specific metric for this.
They did, the forgetting metric, or FG. It's basically the average drop in performance on those general knowledge tests. Any value above 0 means, yep, forgetting has occurred.
Okay, so let's dig into that. Of those 3 big areas, domain knowledge, reasoning, and reading comprehension, which one took the biggest hit? Where was the Achilles heel?
The results were pretty stark. Reading comprehension suffered by far the most significant loss.
Really?
Yeah. That was followed by domain knowledge. And, kind of surprisingly, reasoning was the most resilient of the 3.
Huh. That feels a little backwards to me. You'd think something like logic or math would be fragile, but reading seems so fundamental. Why would that be easier to break?
It's a great question. It probably has to do with how distributed these skills are in the network. Reasoning, like math, might rely on these very specific condensed pathways. They're like well-worn grooves.
Okay.
But reading comprehension relies on this huge interconnected web of nuance, context, and analogy. When you fine-tune the model to do something like generate a punchy headline, you're changing its entire relationship with language.
You're forcing it to prioritize brevity over subtlety. You're overriding the nuance parameters.
Exactly, and you can see it in the numbers. For the BLOOMZ 7.1b model, the FG for reading comprehension was 26.75%.
Wow, so it lost over a quarter of its ability in that area.
A quarter. Compare that to about 18% for domain knowledge and under 14% for reasoning. Specializing the model just hammers its ability to deeply understand text.
That is a massive finding for anyone using an LLM for, say, summarization or analysis. You might get a tool that's better at one thing, but it's a much dumber reader overall.
Precisely. Which brings us to what might be the most paradoxical part of the whole study. We all kind of assume that bigger's better, right? That bigger models are more robust.
Yeah, more stable, harder to break.
Well, this study found the exact opposite.
Okay, let's unpack that, because that's the core counterintuitive finding here. You're saying as the models got bigger, the forgetting actually got worse.
It intensified. That's the paradox of scale they found. There was this clear, consistent trend. As the model size went from 1 billion up to 7 billion parameters, the severity of the knowledge loss grew right alongside it.
Okay, I need the mechanism here. This goes against the whole scale is all you need mantra. Why would the biggest, most powerful model suffer the worst memory loss?
Let's just look at the data for domain knowledge for a second. The smallest BLOOMZ model, the 1.1 billion parameter one, had a forgetting metric of about 9.5%.
Okay, so it lost about 10%.
Right. But the big one, the 7.1 billion parameter BLOOMZ, had an FG of 18.37%, nearly double. It's suffering a much, much more drastic loss.
So what's the hypothesis? Why the huge jump?
The researchers think it all comes down to the starting point. It's about how good the model was before the fine-tuning started. Think of the 7.1B model as an Olympic diver.
I'm with you, and the 1.1B model is an amateur.
Exactly. The Olympic diver starts with incredible performance, a very high initial score, right? But the key finding is that after you put them both through this continual tuning, which is like throwing them both in a shallow pool and telling them to learn a new swimming stroke.
Right, totally different task.
Their final performance on diving tends to end up at a similar, much lower level.
Ah, I see. So they both end up struggling in the shallow water, but the Olympian had a much, much longer way to fall.
That's it, exactly. Their final performance is pretty close, but because the bigger model started from such a high peak, its performance degradation, the thing the FG metric actually measures, is just massive.
That's such a critical distinction. It's not that the big model ends up dumber than the small one, but the trauma of specialization wipes out a much larger chunk of its initial brilliance.
You've got it. That pre-trained strength that you paid so much for is getting functionally erased by the fine-tuning process. Its general utility gets knocked down to something closer to a much smaller model.
Okay, but let me push back on that. If the end result is similar anyway, why should a developer care that the bigger model fell further? Isn't it just about the final performance?
It matters because that steep drop tells you the specialization required a huge disruptive change to the model's parameters. And second, you often need that general knowledge as a buffer for unexpected out-of-domain questions. If that buffer is gone, your whole application becomes brittle.
The safety net is gone.
That makes perfect sense.
Okay, so moving on from scale, what about the blueprint? Did the actual architecture of the model make a difference?
It absolutely did. The study directly compared decoder-only models like BLOOMZ with encoder-decoder models like MT0.
Just as a quick refresher for everyone, encoder-decoder sort of process the input, create a representation, and then decode an output. Decoder-only models, like GPT, are more focused on just generating the next word in a sequence.
A great summary. And in the knowledge retention challenge, there was a clear winner.
Which was?
The decoder-only architecture. At similar sizes, say the BLOOMZ 3B versus the MT0 3.7B, the BLOOMZ model consistently suffered less forgetting.
Do you have a number on that?
Sure. For the reasoning tasks, the BLOOMZ 3B model had an FG of about 11. The MT0 model, however, was way up at 16.7. That's a pretty significant gap in favor of the decoder-only design.
So the implication is that the architecture that's constantly focused on generating the next token is somehow better at protecting its foundational knowledge from being overwritten.
That's the strong suggestion. It seems to handle the trauma of fine-tuning with less damage to its general knowledge base. That's a huge piece of information for anyone choosing a base model for a new project.
Okay, so we have this widespread forgetting. It gets worse with scale, and architecture matters.
Yeah.
Is there any good news in all of this? Any silver linings or ways to fight back?
Actually, yes. Two very encouraging things. The first was a totally unexpected positive side effect related to model bias.
Bias. How does that fit in?
Well, they measured the model's inherent biases, stereotypical associations about gender, race, religion, that kind of thing.
Wait, so fine-tuning it on text simplification somehow made it less biased?
That's exactly what they found. The biases that the models learned from the raw internet during pre-training were actually mitigated during the instruction tuning. The bias scores went down significantly.
That's fascinating. So a positive FG score for bias is actually a good thing. It means the model is forgetting its stereotypes.
You got it. For BLOOMZ 7.1b, its preference for stereotypical sentences dropped by over 11 percentage points. It's this almost accidental benefit of forcing the model into a more structured, formal, and neutral mode of communication.
A huge bonus. But what about actually mitigating the knowledge loss? What strategies worked?
The main one they identified was something we can call pre-tuning protection. They compared the base Llama 7B model to Alpaca 7B. Now, Alpaca is just Llama, but it went through a round of general instruction tuning before the study's experiments.
Ah, so llama was the raw, untrained brain, and alpaca was the brain that already went to a general finishing school.
That's the perfect analogy. And they found that Alpaca, because it had that diverse general training beforehand, was way better at retaining its knowledge during the later specialized tuning. It was already hardened against the trauma.
So if you give your model a solid general-purpose instructional foundation first, it acts like a protective layer against future specialization.
It's like a buffer. They even showed that mixing a tiny amount of general instruction data back into the specialized tuning helped protect the base models too. It's like giving it a little refresher course along the way.
This gives us a really clear set of takeaways. So for you listening, catastrophic forgetting is definitely real. And counterintuitively, bigger models, up to 7 billion parameters, actually show a bigger drop in performance, mostly because they start from a much higher place.
Yeah, in terms of architecture, the decoder-only design seems to be more robust at holding on to what it knows compared to decoder models.
The bottom line for anyone building with these is you have to be vigilant. That initial genius of a massive pre-trained model can be severely degraded by narrow fine-tuning, making it less reliable for general tasks.
Which leads us right to the final provocative thought. The study, it was limited to models up to 7 billion parameters, but their whole hypothesis is that the forgetting rate is driven by how far the model has to fall.
Right, so what happens next?
What happens when we run this same analysis on the true giants? The models that are 10 or 100 times larger, 70 billion parameters or more, will that trend of intensifying forgetting continue on that upward line?
Or could they be so immense, so capacious, that they can learn a new task with such tiny parameter changes that the forgetting trend finally flatlines, or maybe even reverses?
It's the big open question. Does extreme scale eventually make these models trauma-proof? Something we'll all be watching for.